Oh, hey everybody, Mike here. I'm getting ready to start your video, but I'm on hold with Rural King. I'm in position 4 in the queue. Now, I started at position 18 and it took me about 12 minutes
Your call is very important to us. Please hold for the next available representative.
to get through 12 minutes to get...
You are at queue position 3.
Oh, I'm in 3 in the queue. Anyhow, it's taken me about a minute to get through each spot, so I got 3 minutes, and then I could start your video. So, because I determined the rate of me moving through the queue at about a position a minute, and that's the whole thing, is we want to be able to predict things with the past rates, and that's what we're going to talk about today. I got to go because I'm in position 3. I'm getting nervous. Well, howdy partners, howdy. Mike here, and today we're going to talk about the effect of concentration on rate. Actually, we'll be talking about that for quite a while. So here's what we sometimes need to do is understand how the reaction responds to changes in concentration. These things are called, these relationships that we try to figure out, they're like little puzzles, are called rate laws. So let's take this reaction here where you take ClO2 and react it with OH. And you know what the funny thing is? We'll never have to really worry about what the products are. What we're going to do is mess with the concentration of the reactants and see what happens to the rate. So this whole thing is called a rate law. I'll just point to the whole big old thing. That's called a rate law or rate relationship. Basically what you've got here is you've got something called a constant. This is called a rate constant, and it's always given the symbol K. And the units of the rate constant can vary depending on what the orders are. These are called orders. What these exponents are orders, and they are usually a 0, a 1, or a 2. Now, I can't really tell you everything that we're going to get into without complicating it, so just trust me, there's about 3 ways the reaction can unfold, or the story of the reaction. And if those exponents, x and y, are a 1 or a 2, it tells a lot. And I'll just say this for 20 seconds. There's some reactions where molecule 1 has to collide with a molecule of itself, another molecule, or there's some reactions where the molecules just fall apart. And that determines what that exponent is, a 1 or 2, or even a 0. So this is the rate here. So this is the progress in the change in concentration over change in time. So this is usually in moles per liter per time. And the units of time can vary. So what we're going to do is we're going to plug in different concentrations and watch how the rate changes. And if we say double or triple this, then the rate itself will either double or triple, or sometimes to the square of that, or sometimes to the nothing. If it's a 0 exponent here, that means it just becomes a 1, and that means that that particular component doesn't even change the rate of a reaction, and that happens at times, and there's reasons we'll talk about. So what you do is you get presented with a whole bunch of data that looks like this. Now that can look really overwhelming, I'm sure, but what we need to do is sort of isolate our variables. So we do this kind of thing every day, and we could say, hey, how come I lost 5 pounds? Well, is it because I started running, or is it because I changed my diet? And that's because you got 2 variables changing at the same time, so you never can figure it out. So what we're going to do is we're going to look at these 3 experiments where the concentration of something changed and see how it affects the rate. And like I said before, you don't want to change too many variables at once. So I'm going to look at the first 2 experiments and look at what happens to the concentration. I can see that this is constant, 0.03 in experiment 2, doesn't change, it's 0.03 in experiment 1. But you see what I can see happening here is between experiment 2 and experiment 1, that was a threefold change in the concentration. And what do you know? It sped up the rate. But if I go do a little bit of math and I divide that number by the smaller number, 0.0248, go ahead and do it along with me. Divided by 0.00827, that is 2.9987 times. That's also 3x. So what did we figure out here? What did we glean from this? That if I changed the concentration of this threefold and I kept this constant, then that changed threefold. So let's go see what happens if we put these numbers into here. So what happened is I changed ClO2 by a factor of threefold. That changed by a factor of threefold. That means that exponent is 1. See, that also tells me that if I change this by a factor of 9, or just I'll make up some number, that tells me that if I change this number and say quadrupled it, this would also quadruple. So that means x here is, this is what we figured out from just looking at the pattern, x is an exponent of 1. Whatever factor that concentration changed by, if you hold the concentration of OH minus constant, x is 1 because it changed proportionally. So not only did it tell us that if we tripled that concentration and we tripled the rate, I could have increased the concentration by tenfold, and so the rate would do the same thing. And so you see what we're doing is we're just extrapolating the pattern that we see. So now what I'm going to do is I've kind of solved the puzzle for what x is. Let's find out what y is, which means I'm going to change the concentration, or they changed the concentration OH minus where the other component didn't change. Now I wouldn't want to look at 1 and 3 because you got experiments 1 and 3, you got two variables changing. But if I look at experiments 2 and 3, you can see that the concentration of ClO2 is constant. And I always like to think of things increasing. So if I go from 2 to 3, that's a threefold change. And what happened over here? Another threefold change. So now y did basically the same thing. And that is that y is 1. So now that gives us permission from the universe to say that because we just looked at those 3 experiments where I messed around with the concentrations and see what happens to rate, I say now, I can write this all over again in a more specific fashion, right? Rate equals K times ClO2, now to the 1 power. Of course, you know, sometimes we leave it off when it's the power 1, but I'm putting it in here to be more explicit. And now what that lets us do is go find what K is. See, these are rates, and then I could then go ahead and plug it in, and why don't we do that? Now I'm getting rid of another variable. I can go solve for K, and so I would find K by just dividing rate, divide both sides by those concentrations, right? So rate divided by the concentration of ClO2 to the first power divided by OH minus to the first power. And then you'd say, well, geez, how do I figure out what K is? Well, you take some numbers and stick it in there. And then you might say, well, which one do I do? Experiment 1, 2, or 3? And the answer is yes, whatever one you want to do. They're all part of the same system. They're all basically giving you the same information back here. They're part of the big old system of this reaction. And if you plugged in numbers for 1, 2, or 3, you would get the same number. And so what I'm going to ask you to do then, why don't you, I'm going to plug in the numbers for experiment 3. You go plug in the numbers for experiment 1 or 2 or whatever you want to do. But I'm going to go ahead, 0.0248. I'm going to put my units in here and be a good example, moles per liter per second. And then I'm going to divide by the concentration of, now remember these brackets mean moles per liter, so 0.020 moles per liter to the first power, and then divided by 0.090 moles per liter. And then we're going to get a number. Oh, and what's the units going to be? Well, this moles per liter canceled out by that moles per liter. It's going to be liters per mole per second. And that tells you something that I will get to here. But let me crank out a number. 0.0248 divided by 0.020 divided by 0.090. And I get a K of 13.8. And so now what we could do is, if there was some sort of future experiment we were going to do, 13.8. K equals 13.8. We could plug that in. Liters per mole per second. And we could go crank that in. You know, we could say rate is equal to 13.8 liters per mole per second. And then, you know, we could say, well, what would the rate be if this was we'll take something that's smaller than everything, 0.01 times 0.01. Now you know that would then be, well, I don't know why I'm so paranoid. I could do that one in my head, but so this would be 0.00138. And by the way, those would be moles per liter. And so the liters per mole would cancel one of the moles per liter, and it would be moles per liter per second, which is concentration change divided by time. And then you could look at that and you could say, well, does that make sense? Yeah, you know, it's well lower in concentration than the two numbers were up here, and I got a much lower rate. So that's the whole gist of what we're trying to do here, is we're trying to go ahead, mess with the concentration, observe it, and then extrapolate from that to get this thing right here, folks, the rate law. And from the rate law, you can calculate K, and then from K you could calculate a future rate. And the only thing is, you got to have the luxury of having all these concentrations in separate containers. And so, you know, if you have the privilege of having all these compounds at your disposal, you can do an experiment like that and determine what order it is. And by the way, sometimes when they have something like a rate law, they add the orders and they say this is second order overall, because you just add the powers. Or they would say that this is first order with respect to ClO2, and first order with respect to OH minus. And so, and they call it a rate law because it's reproducible. So let's try another one that has a little bit higher difficulty factor next. All right, here goes another one. What I'm going to do is just show you that even if you are having a hard time getting started, the thing you can do next is you can then write a basic form of a rate law. So I could say, here's my two reactants, H2 and NO, and I could say, well, the rate law is going to look like this. Rate equals K, don't know what K is yet, times H2 to some power, don't know what the power is yet. We could just call it A and B, or X and Y, whatever you want to call it. Let's call it X, times NO to the Y. And the name of the game is find out what X and Y are first, or else you can't find K. And so here's one that I pulled out of a textbook from somewhere. And there's more examples in the OpenStax textbook, but I just went and took some obscure textbook. And let me tell you a little bit of advice here. To keep yourself sane, watch out for this power of 10 stuff. So the writer of the homework problem will want to throw you a curveball. I don't know, sometimes they're very frustrated people. But what they'll do is they'll throw you this power of 10 stuff, and so make all these the same power of 10. So what I'm going to do is I'm going to call this 0.2835 times 10 to the minus 2. And that way everything's at times 10 to the minus 2, and now you can just ignore the the times 10 to the minus 2 or 3, and they're all negative 2's, and you can just look at the number in front of it. And so now what I'm going to do, same strategy as before, I'm going to go and look at, I don't know, the first two experiments seem to jump out at me just because they're the first two. H2 is being held constant. NO is doubling. Last example, everything tripled, but it doesn't matter. There's no formula for it. And now what's happening here between 0.2835 times 10 to the minus 2 and 1.134? So what I'm just going to do is I'm just going to divide the bigger number by the smaller number. 1.134 divided by 0.2835. That is 4. So 4 is 2 squared. And so what we just figured out is that the Y, the concentration change, what we figured out here, the concentration doubled, the rate quadrupled, and therefore that we just proved that whatever change you do to NO, triple, for example, if you tripled it, you would then increase the rate by 3 squared, or 9 times. So you see the rate here actually didn't change proportionally like the last example. It changed to the square of the change of the concentration. That is what we call second order with respect to NO. Fair enough? And now what we got here is we're done with that one. We can look at this here. That doubled. This is constant. What happened here? That doubled. 2.268 is, and so that's a proportional change. That doubled, so did that. That means X. Now make sure you don't get them mixed up. So we're talking about the thing changing. That's where the exponent is being determined. X is 1. So now we can rewrite that whole thing with the new exponents in there. And that's a new rate law. And we could say rate equals K times concentration of H2. Careful now, don't get them mixed up, to the first power times concentration of NO to the second power. And that's the new rate equation or rate law. And then if you were if this really turns you on, you could even say, well, geez, according to that, if that doubled and so did that at the same time, then that would make the rate change by a factor of this. This doubling would make the rate quadruple. This doubling would make the rate double. And so quadruple times double is times to the 8 times. You know, it increased by 8. It octupled. I just made that word up, octupled. So the rate changed by a factor of 2 here and a factor of 2 there. And, you add those exponents up. You throw a, twofold here, just make it twofold change in the rate. Twofold here change would make quadrupling the rate, and then you compound those, that would be an 8-fold change in the rate. And if you took this number here, divided by that, it's 8-fold. But what you could do here is you could go, and now a lot of these problems they'll say, go calculate K. And then if last example we used it, so I could say K is equal to the rate divided by concentration H2 to the first power divided by concentration NO squared, and then plug in your favorite numbers. Just like last time, maybe you go plug in number 3, I'll plug in number 2, so it'd be number 1, 2.835 times 10 to the minus 3 moles per liter per second, divided by, now you got to use the numbers here, 0.35 moles per liter, divided by 0.30 moles per liter, but this one gets squared, and then we crank out a number. Oh, by the way, the units would be different, but let's get a number first. So 2.835 times 10 to the minus 3 divided by 0.35 to the first power, divided by 0.03, divided by 0.03 again because it's squared, equals 9. So this would be the rate constant's value is 9.0 times, no, just 9.0 is what I got. The units would be, those moles per liter cancel, but it would actually be seconds in the denominator here, but then this goes up into the numerator, so it would be liters squared, moles squared per second. Now, this is a little helpful hint that I'm going to tell you. I think it's always funny when the homework problem, and you know, now we live in the age of this online homework where there's a box in there and you got to fill it in. But do you notice how last time the units were liters per mole per second? Those are the units you always get when it's second order overall. This was third order overall. And you notice we had different units because we divided by moles per liter another time. So, quite the tell if you're a poker player is that the units of the rate constant tell you what the overall order is, and then later on we're going to move on from doing this where we change the concentration. We're going to look at different equations to describe the curves, but the units of K give you kind of part of the answer because you can tell by every time it's third order overall you get those units, so you got a little hint there. And then so what I was saying about online homework, there'll be a box there, but then to the right they'll tell you the units, and that's a complete giveaway in some cases because the units of K vary depending on what those exponents are. Folks, this is meaty stuff. I would try to do 3 examples, but I don't think it's going to be very palatable. Take a break and give some of these a try on your own and see if we've done everything you could, except here we didn't crank the rate out like we did the first one. But find the orders, find the rate law, calculate K, stick it back in, find the rate at some other concentration. That's about all that can be done with this phase of talking about kinetics. Next time, we're going to whip out some logarithms. And so you might want to review those if you're not comfortable with logarithms, particularly natural logs, which sound like some sort of lumber without preservatives, but it's a way to describe curves. So buckle up, it gets mathy in here. Some of you like that, some of you don't, but just got to tolerate it. See you next time. Bye.